Good morning, friends. About refrigeration and air conditioning, the best books available in the market are by Professor C.P. Arora, by Professor P.L. Balani. These are the two simple, very concise form good books available in the market. Let us start with refrigeration. By the term refrigeration, we mean production of cold. And the coldness can be produced because of the abstraction of heat. That means from the given objects, if we remove heat, we are producing coldness. And production of coldness shall mean we are producing refrigeration. When we talk of abstraction of heat, we talk of a cycle on which the given machine shall be assumed to operate. And whenever we think of a cycle, the first idea comes in the mind is for the Carnot cycle. And Carnot cycle is a reversible cycle used for a heat engine. When we reverse it, the reversed Carnot cycle, that shall be applicable for a heat pump or for a refrigerator. To revise our memories, let us think of Carnot cycle, then we will reverse it, and that will be applicable for a refrigerator or for a heat pump. And then we will be studying in details what shall we mean by a refrigerator or by a heat pump. Carnot cycle applicable for a heat engine. Let us represent the various processes on PV diagram. As well as TS diagram. On PV diagram, heat is supplied at constant high temperature heat is supplied at constant high temperature. As heat is supplied, entropy must increase. After heat addition, there is expansion, isentropic. Isentropic expansion will mean entropy remaining constant, pressure and temperature shall tend to decrease. Then heat is rejected at the constant low temperature. As heat is rejected, entropy should decrease, temperature remaining constant. And lastly, there is a process of compression which is isentropic. All the four processes are reversible processes. So the Carnot cycle is a reversible cycle. One to two, heat is supplied. It is given by area under the curve. That means it is TH into S2 minus S1. Two to three, process is isentropic, no heat transfer. Then 3 to 4, heat is rejected. Which is area under the curve. That is TL into S3 minus S4. 4 to 1 being isentropic, no heat transfer. Net work done, heat supplied minus heat rejected, that is TH into S2 minus S1 minus TL into S3 minus S4. Carnot efficiency, the ratio of net work done and heat supplied. TH into S2 minus S1 minus TL into S3 minus S4 upon TH into S2 minus S1. It becomes 1 minus TL into S3 minus S4 upon TH into S2 minus S1. And this becomes 1 minus TL upon TH. Because S3 minus S4 is equal to S2 minus S1. Now let us see the reverse Carnot cycle. PV diagram and TS diagram. At higher temperature, heat was supplied. Now at higher temperature TH, heat should be rejected. So that it becomes a reverse process. Then it was adiabatic expansion. Now it should be adiabatic compression. Earlier it was heat rejected at low temperature. Now it should be heat abstracted at lower temperature. Earlier heat was rejected, now heat should be abstracted. And then the process is isentropic. At higher temperature, heat is rejected. It is isentropic compression. Heat is abstracted at lower temperature. And then there is isentropic expansion. If low temperature is the requirement, we call it as refrigerator. What is the output? Output is the cooling effect. Which is TL into delta S. How much is input? Work required. That means heat rejected minus heat abstracted. Heat rejected is TH into delta S. Heat abstracted is TL into delta S. That means TH minus TL into delta S. Ratio of output and input. Output is TL into delta S, the cooling effect. The work required is the input TH minus TL into delta S. And this becomes TL upon TH minus TL. And this ratio we call as COP. The coefficient of performance. If TH is the requirement, we'll be calling it as the heat pump. And the COP of the heat pump, output upon input. Now output is the heating effect. Input is the work required to run the system. And now the heating effect corresponds to TH into delta S. And work required is TH minus TL into delta S. And that becomes TH upon TH minus TL. Easy way to remember, higher temperature is a requirement. Numerator shall be higher temperature and it shall be called as heat pump. If low temperature is a requirement, TL shall be in the numerator and TL upon TH minus TL. It will be the case of the refrigerator. Now, any point which is not clear? I hope it is all okay. Now let us see in what unit the refrigeration is expressed. In olden days, the refrigeration, the cooling effect was produced due to the melting of ice. In rivers, in small lakes, during winter, water gets frozen to ice, and that ice is cut into some slabs and is maintained in insulated boxes so that whenever refrigeration is required, we can have the ice, and because of the melting of the ice, the cooling effect shall be produced. The biggest slab of ice ever cut in those days, by mistake, it was called as 1 ton of ice. I've used the term by mistake. We were calling it as 1 ton of ice. At atmospheric pressure, the temperature of the ice is 32 degree Fahrenheit or 0 degree centigrade. If this ton of ice is to melt, for melting, heat is required, and that heat is picked up from the surrounding. When heat is picked up from the surroundings, in the surroundings, cooling effect is produced. If this cooling effect is produced in 24 hours, that cooling effect we used to call as 1 TR. That is 1 ton of refrigeration. Now, time is coming into the picture. The latent heat picked up from the surroundings at 0 degree centigrade is coming into the picture. And this amount, 1 ton, is coming into the picture. When they weighed this ton, unfortunately, it was 2,000 pounds. 2,240 pounds is 1 ton. And by mistake, this 2,000 pound they were calling as 1 ton. Mistake once committed doesn't remain as mistake, and it continues for all the times. So 2,000 pounds of ice, when melts, the latent heat of melting of ice is 144 BTU per pound. Pound cancels. So many BTUs in how much time? 24 hours. So 24 into 6. So that means it is 12,000 BTU per hour. The term BTU stands for British Thermal Unit. BTU term was used in FPA system. Now in MK system, we use kilocalorie. And 80 kilocalories per kg is the latent heat of melting of ice. And 2000 pounds, when converted to kg, 2.2046 pound is 1 kg. So this gets converted to kg into 80 kilocalorie per kg. This much is the cooling effect produced in 24 hours. It is 3023.98 kilocalorie per hour. Which is 50.4 kilocalories per minute, which is normally taken as 50 kilocalories per minute. If we take 50 kilocalories per minute, then it becomes 3000 kilocalories per hour. But actually the figure is 3023.98, which should be taken as 3024 kilocalories per hour. Hence, it is not recommended to take it as 50. No doubt, some of the textbooks take it as 50. And then for hour, they take it as 3000. That means inherent, we are making some error. So to be very, very accurate, we should either take 3024 or 50.4 and not 50 or 3000. And these days, even we don't talk in terms of kilocalories, we talk in terms of kilowatt. £2,000, 2.2046 becomes kg. 80 kilocalorie per kg gets converted to kilocalories multiplied by 4.1868 kilojoule per kilocalorie. It becomes kilojoules divided by 24 per hour divided by 60 per minute divided by 60 per second. Because when we write heat units in kilojoules, we take time in SI units as second, so that we write kilojoule per second, which is kilowatt. Which is 3.51688. We may take it as 3.517 kilowatt. It is 211.01 kilojoule per minute. And many authors round it off to 3.5 kilowatt. If we take 3.5 kilowatt, it will become 210 kilojoule per minute. So some books, they take it as 210, some books take it as 211. So either we should go in for 3.517 and 211 and not 210. Any point requiring clarification? For being quite elementary, I hope all of you are quite clear. The reverse Carnot cycle, which we talked about for refrigerator or the heat pump. This cycle we consider as an ideal cycle. In ideal cycle, the ideal working substance is taken as air. Here the specific heat value is very small. So when we think of a practical cycle, we take a refrigerant whose specific heat is quite high, and working substance shall be liquid and vapors. These refrigerants are chlorofluorocarbons. They are basically halogenated derivatives of alkanes. Alkanes means methane, ethane, propane, etc. General formula, we take CmHnFpClQ. Carbon, hydrogen, fluorine and chlorine. (2m plus 2 should be N plus P plus Q. If it holds good, then the refrigerant is designated as R M minus 1 N plus 1 P. For example, R022 means m minus 1 should be 0, n plus 1 should be 2, p should be 2. That means m is equal to 1, n is equal to 1, p is equal to 2. What should be q? Q should be such that 2m plus 2 is n plus p plus q. 2m, 2 plus 2, 4 is equal to n, 1, p, 2 plus q. Therefore, q should be 1. So it should be C, M. M is 1. 1 we don't write. H, N, 1. F, P. P is 2. Cl, Q. Q is 1. That means it is a derivative of methane. 4H, 1H, 2 and 1, 3. So I may call it as monochloro difluoromethane. Now you try for R13. What it should be. अंदर किसी को भेजना गड़बड़ हो गई. अच्छा इसमें प्रॉब्लम हो रही है. Any clarification required? I have given you the exercise to see the chemical name of R13. What you are required to do, this nomenclature or m minus 1, n plus 1, p. That means m minus 1 is 0, n plus 1 is 1, p is 3. That means m is equal to 1, n is equal to 0, p is equal to 3. What should be q? For q, 2m plus 2 should be n plus p plus q. 2m plus 2 is 4, n is 0, p is 3, so q shall be 1. That means Cm, C1, H0, Fp3, Clq1. That means this is again a derivative of methane. 3 and 1, 4. So that means this is monochloro trifluoro methane. I hope it should be clear. Last, difluoromethane. What is its number? Many a times the number is given, you have to find out the chemical name. And sometimes chemical name is given, you have to find out the relevant number. Difluoro. Methane, C is 1. That means it should be derivative of methane. So it should be CH2F2. we have to compare it with CmHnFpCl3. M is 1, hydrogen N is 2, fluorine P is 2, and Q is 0. There is no chlorine. Let us check up whether it is a refrigerant or not. That will mean 2m plus 2 should be N plus P plus Q. 2m, 2 and 2, 4. This is N, 2, P, 2, Q, and Q is 0. That matches. What should be its nomenclature? Or m minus 1 n plus 1 p, or m minus 1 1 minus 1 0, n plus 1 2 and 1 3, p 2. So R32 is difluoromethane. Still, any clarification needed? Write down a question. A heat pump absorbs 10 kilowatt of heat from outside environment at 250 Kelvin while absorbing 15 kilowatt of work. It delivers heat to a room that must be kept warm at 300 Kelvin. What is the coefficient of performance of the heat pump? There is a heat pump surroundings are at 250 Kelvin. It is absorbing 10 kilowatt of heat. It requires 15 kilowatt of work. Then it delivers heat to warm up a room at 300 Kelvin. Its COP we are interested to get. 10 kilowatt of heat it is picking up, 15 kilowatt as work is added to it, total becomes 25 kilowatt which is supplied to the room. COP is heating effect upon work required. Heating effect is 25 kilowatt. Work required is 15 kilowatt. $1.67 becomes the COP. Energy can neither be created nor destroyed, will get converted from one form into the other. This 15 kilowatt of work is getting converted to heat, plus this 10 kilowatt of heat put together becomes 25 kilowatt of energy that is supplied to the room to be maintained at 300 Kelvin. So this heating effect becomes the output. This 15 kilowatt is the input. One cannot imagine that such a simple type of question can also be asked in GATE. The COP of a Carnot heat pump operating between 6 degrees centigrade and 37 degrees centigrade is When the name stated is Carnot, COP for the heat pump, H in the numerator, higher temperature is our requirement. The students may commit the mistake of putting it at 37 and TL as 6, which may be wrong. And the last question, it was not stated as Carnot cycle. So we couldn't use TH upon TH minus TL. We had to use the given values. Another question. The heat removal rate from a refrigerated space and power input to the compressor are 7.2 kilowatt and 1.8 kilowatt respectively. The coefficient of performance of the refrigerator is refrigerator means requirement is the low temperature. That means cooling effect upon work required. Cooling effect heat removal rate 7.2 kilowatt, corresponding work required is 1.8 kilowatt. So 4 is the COP of the refrigerator. Any other question from your side based on reverse Carnot cycle or the data available, whether it is a refrigerator or a heat pump? ASHRAE is the largest society internationally. It is American Society for Heating, Refrigerating and Air Conditioning Engineers. The nomenclature which I had given you, CM, HN, FP, CLQ, condition to be satisfied, 2M plus 2 is N plus P plus Q, and it is R M minus 1 N plus 1 P. This is for organic compounds. For inorganic compounds like water, carbon dioxide, ammonia, we write R7 and then the molecular weight. For example, water R718, carbon dioxide R744, ammonia R717. Air R729. Sulfur dioxide R764. More complicated things we'll see whenever required. At present, it is sufficient to understand the nomenclature for organic and inorganic compounds. I hope all okay. So, we can break for 15 minutes.